This paper presents a novel approach to enhancing the robustness of vehicle motion prediction models by leveraging a Frenet frame wrapper. The proposed method addresses the generalization problem in trajectory prediction tasks, which is often overlooked in state-of-the-art, sotA, models. By representing model inputs and outputs in a Frenet frame defined by lane centerline sequences, the authors aim to promote lane following and reduce off-road predictions in challenging scenarios. The Frenet frame has been widely used in planning and prediction tasks, as it decomposes trajectories into their progress along a reference lane and lateral displacement across it. However, few data-driven prediction models have adopted this representation. The authors propose a general wrapper that can be applied to sotA models without altering their architecture, allowing for the analysis of the trade-off between prediction accuracy and generalization induced by this representation. The method consists of assigning the target vehicle to a lane centerline, identifying relevant lane centerline sequences, transforming the scene representation into the Frenet frame of each centerline, querying the prediction model to obtain trajectories for each centerline, and finally, forming the final set of output trajectories by suppressing near-duplicate trajectories and selecting trajectories based on their probabilities. The authors use a benchmarking methodology introduced in 15 to evaluate their approach and demonstrate that integrating sotA prediction models in a Frenet wrapper reduces off-road predictions by over 90%. The experiments involved two sotA motion prediction models, showcasing the effectiveness of this approach. This work contributes to the field of robust motion prediction by introducing a general, model-agnostic Frenet frame wrapper that can be applied to various sotA prediction models. It highlights the trade-off between prediction accuracy and generalization and demonstrates how the Frenet representation can significantly enhance the robustness of vehicle motion prediction models. The research paper discusses a novel approach to improve the accuracy and robustness of lane-following models by transforming the scene into the Frenet frame of each centerline. This transformation allows the model to better understand the lane context and predict future motion more effectively. The method is evaluated on the Argoverse dataset and the scene attack benchmark, showing competitive results with Cartesian models in terms of displacement errors and off-road probability. However, the Frenet wrapper models exhibit higher diversity in predicted trajectories, indicating a better ability to adapt to complex scenarios. The paper also presents several baselines, including training with dropouts and without motion history, to further emphasize the benefits of the Frenet frame approach. Overall, the study demonstrates the potential of using the Frenet frame to enhance the performance and robustness of lane-following models, particularly in corner cases where Cartesian models may struggle. Here is a combined summary of the 2 pages. The authors evaluate the robustness of their proposed Frenet wrapper on perturbed scenes, demonstrating its effectiveness in improving generalization capabilities. Fig. 2 illustrates scene attack perturbations, where 3 transformations are applied to the original scene, creating turns at a fixed distance ahead of the target vehicle. The motion history and ground truth are slowed down to account for the large curvature. In the comparison on perturbed scenes, the authors analyze the results on the scene attack benchmark, evaluating the robustness of the models under map perturbations. They observed that displacement errors and off-road probabilities increase drastically for Cartesian models when perturbing the scenes, whereas SD models are much more robust, with off-road probabilities only increasing by 2.5 percentage points. Neither dropouts in training nor removing the motion history entirely from the features make the models more robust. The SD models outperform all baselines by a large margin, resulting in a new state-of-the-art on the scene attack benchmark. The qualitative results in Fig. 3 demonstrate how SD models generalize seamlessly to perturbed scenes, whereas Cartesian models fail to adapt. The remaining off-road predictions of SD models are mostly caused by corner cases in the identification of relevant centerlines. The models partially compensate for this by also following other lanes than the reference lane of the coordinate frame. The authors also present the results of their experiments in Table 2, which compares the performance of different models on perturbed scenes. The results show that SD models significantly outperform Cartesian models, with lower displacement errors and off-road probabilities. The authors conclude that representing the input and output of prediction models in the Frenet frame improves generalization to challenging scenarios by a large margin, reducing predicted off-road probability by over 90% on the scene attack benchmark. The evaluation committee member provides a detailed summary of the research paper, focusing on the technical aspects and key findings. The summary starts by highlighting the importance of integrating prediction and planning in deep learning-based autonomous driving systems, referencing various papers including Rethinking Integration of Prediction and Planning in Deep Learning-Based Automated Driving Systems, a review. It then delves into the methodology of the paper, explaining the use of multipath++ and lane GCN models for trajectory prediction, and how they are evaluated with different centerline aggregation methods. The summary emphasizes the significance of accurate estimation of the prior over the lanes, citing the privileged prior model as an upper bound. It also discusses the results of various ablations, including uniform prior, lane scoring, clustering, and greedy sampling, highlighting the improvements in displacement errors and miss rate achieved by these methods. The summary concludes by emphasizing the importance of selecting the optimal set of trajectories for accurate prediction and planning in autonomous driving systems.